So, good evening students. I hope you can hear me and you can see the screen clearly. So, straight away we go for the discussion of the solutions of this XCE, basically the thermodynamics of GATE 2021 XE paper. So, we'll see basically the detailed solutions and also we'll check the key that's available first. Clear? So, let us straight away go for solving the questions. So, because there will be total 22 questions and of course 9 1 mark and 18 2 mark, 13 2 mark questions. So, definitely totally they will constitute for a total of 35 marks, correct? So, let us go for the things straight away. So, let us try to solve this first question. Okay. So, let us straight away solve the questions. So, a refrigerator working on a reversed Carnot cycle has a coefficient of performance COP of 4. So, it's clearly given the refrigerator is working on a reversed Carnot cycle. So, definitely if you try to draw the Carnot cycles and if you try to draw the components of the refrigeration cycle, then this is a Carnot refrigerator, which is a refrigerator which by taking some work, of course, this is the minimum work that it takes, and of course, it takes some heat from the low temperature reservoir, which is TL at temperature TL, and it delivers to heat at a high temperature reservoir, which is at TH. So, this is a basic reservoir that works on the reverse Carnot cycle, and of course, these values are given. COP of this is given, and this QL Q dot L general, if you write this as power, W dot minimum, and this Q dot L is nothing but the refrigeration effect that you're going to produce. Correct? So, this is the refrigeration effect. So, by definition, we know that COP is nothing but COP of this Carnot refrigerator. This is equal to TL divided by TH minus TL. But of course, here it's clearly given in terms of heat, in energy ratio. So, COP is equal to 4. This COP is nothing but refrigeration effect that it produces divided by work minimum. Correct? Now, see clearly, if this refrigerator works as a heat pump and consumes 1 kilowatt of power, the heating effect will be. So, this COP or this refrigerator is now operated as a heat pump, and the operating cycles for both refrigerator and heat pump are same. So, now we know this relation, the standard relation, COP of reversible heat pump. This is always equal to COP of reversible refrigerator, or in other words, the Carnot refrigerator plus 1. This is what you have. So, if this is given as 4, then this 4 plus 1 is nothing but COP of the reversible heat pump. Clear? So, this COP of reversible heat pump is equal to 5. So, this COP of the reversible heat pump is equal to 5, and it's clearly given if the heat pump consumes 1 kilowatt of work input. So, the heat or the work input that's consuming by this heat pump is 1 kilowatt. So, if you write the definition, this is Q dot H, which is the heating effect in case of a refrigerator. So, this 5 is equal to Q dot H, which is the heating effect produced by the heat pump divided by the work input. Okay? But of course, this produces this heating effect at a minimum power input. So, it's given if the heat pump is consuming 1 kilowatt. So, this power that the heat pump is consuming is 1 kilowatt. So, if this is 1 kilowatt, so what is the heating effect? So, Q dot H basically is equal to 5 kilowatts. This is what we have. Okay. So, the heating effect that this heat pump produces is nothing but 5 kilowatts, and that's what we have clearly. Okay. So, 5 kilowatts is the answer, and that's in the first option. Okay. So, this question came in GATE 2021 XE. So, this is the first question in the paper. So, we could solve this. Let's go for the next question. So, the liquid phase of a pure substance is termed as dash if its temperature is lower than the saturation temperature corresponding to its pressure P. So, generally it's given it's a pure substance. So, whenever there is a pure substance, we can draw the TS diagram or PV diagram on any other coordinates. So, if the temperature is lower than the saturation pressure, so here they are dealing with temperatures and pressures, correct? So, let us see here. If this is your TS diagram, then you will be getting the dome of the vapor dome in such manner, correct? So, now in this vapor dome, this line is a bit slant as compared to this, because the liquids here to this left we have liquids, and liquids are practically incompressible, and these line they don't diverge much as the pressure increases. So, definitely if you try to draw the constant pressure line at this point, so we have the constant pressure lines, P is equal to constant, correct? Here you need not draw the straight lines, because they don't behave as ideal gases at this vicinity. So, this is how a constant pressure line looks like here. So, they are asking you if the temperature is lower than the saturation temperature corresponding to the same pressure. If this is the saturation pressure curve, then definitely the saturation temperature is somewhere here. This is T saturation, correct? So, if this is T saturation and if your temperature is below this, means somewhere here, then this is a liquid region, and this is called the saturated liquid, and this particular state, this is resembled as subcooled liquid. Okay, we know this TS diagram very much. So subcooled liquid is what we can have here. So this state at the temperature which is slightly lower than this T saturation temperature, but of course lying on the same pressure curve, then this liquid which is here is called the subcooled liquid. So here we have the subcooled liquid as the answer. Flashing liquid is something at this point because it suddenly flashes from liquid state to vapor state without any particular phase change. Okay, so here we call this flashing liquid at this point, which is here, which is somewhere here near to the critical state, so that whenever if you supply little amount of heat, it flashes all of a sudden to its vapor form. Okay, so that's now means for the time being, the answer of this question is subcooled liquid, because this is at a lower pressure but on the same pressure curve. Okay, so let's go for the next question. So here we have a cylinder of volume 0.1 meter cube is filled with 100 moles of propane, which of course the chemical formula, you know, general alkanes are formula CnH2n plus 2. So of course propane is the case when N is equal to 3. So C3H8 at 2 megapascals. If propane is assumed to obey the van der Waals equation of state, then this temperature is dash Kelvin. So basically we will consider this van der Waals equation. So in van der Waals equation we have P plus A by, since we are dealing with moles, let us write molar specific volumes. So V bar square into V bar minus B. This should give you your universal gas constant R bar into T. Correct? So this is what we have. This is the standard van der Waals equation, but of course your volumes are in molar specific volumes. Now let us see what is the total volume of the container. You can identify certain data from the question. Volume is equal to 0.1 meter cube. So volume V is equal to 0.1 meter cube. Okay. Next is filled with 100 moles of propane. So the substance is of 100 moles. So number of moles is equal to 100 moles, which can also be written as 0.1 kilomoles. Correct? So if this is the case, then if you write V bar, then this V bar is equal to 0.1 divided by 0.1. Of course, this is in meter cube and this is in kilomoles. So you can see clearly this gets cancelled and your V bar is equal to 1 meter cube per kilomole. Thank you, Rahul. So see here, 1 meter cube per kilomole. So this is what we have. Now V bar is 1 and here some constants are also given to evaluate this temperatures, correct? So the van der Waals equation for propane are, the van der Waals constants for propane are A is equal to 932.9 meter cube per kilomole square. Kilopascals of course in a multiplication. Now look, why I have converted this V bar into meter cube per kilomoles. This pressure is anyhow which to be substituted in kilopascals, and if you want to add this A plus A by V square term to this P, then definitely the dimensions of this P and this A by V bar square should be same. Okay, so here you might have a doubt why I haven't considered meter cube per mole, but why I have considered meter cube per kilomole, because if you want to add these two quantities, dimensionally they should be same, and the dimensions of this is kilopascals. So if you want to add this constant to this P, then definitely this meter cube per kilomole square has to be cancelled, which means this V bar has to be in the units of meter cube per kilomole. Clear? So that's why we are writing this V bar in meter cube per kilomoles. Okay, so that is 1 meter cube per kilomole. So this is what we have. So let us substitute in the van der Waals equation. So pressure is in kilopascals of course. So 2 megapascals is nothing but 2000 kilopascals plus A by V square. A is 939.2 divided by V square into V minus B, which is 1 minus B is again meter cube per kilomole, so 0.0905. This is equal to your R bar, which is universal gas constant is also given 8.3145 joule per mole Kelvin, or it's also same as kilojoule per kilomole Kelvin. Since we are substituting pressure and this A value in kilopascals, we will write this R value in kilojoule per kilomole Kelvin, which is 8.314 of course. So let us straight away write this R as 8.31. Just a second, some setting has got changed. Yeah, 8.3145 into T. So we need to get the value of T from this equation, and it's a simple equation, only one variable and one equation. So let us try to solve. So 2000 plus 939.2, which is 2939.2. So let us quickly go for a calculator in a Google. Yes, so we have the calculator here. So let us calculate these values. So 2939.2 into, look, we have 1 minus 0.0905. So 1 minus 0.0905. This is what we have. So this divided by this universal gas constant, which is 8.3145. So let us divide this. Divided by 8.3145. This is what we have, and 321.51 is the answer of this temperature in Kelvin. So T is equal to 321.51 Kelvin, and that's what they are exactly asking at this particular state. What is the temperature is in Kelvin. This is 321.51 Kelvin, of course. Okay, so this is the absolute temperature at which this gas is situated. That's obeying the van der Waals equation with this particular situations here. Clear? So this is 321.51. Next, let us go for the next question. This is a very simple question actually. So see here, two identical pressure cookers, cooker A and cooker B, each having a total internal capacity of 6 liters are available. So you can clearly see the capacity of this cooker is 6 liters, and of course the capacity of this cooker is also 6 liters. Now, cooker A is filled with 2 liters of liquid water at 110 degrees Celsius. So what's the temperature of this? 110 degrees Celsius, and of course this is 2 liters. Next, and cooker B is filled with 4 liters of liquid water at 110 degrees Celsius. As you can see, liquid level is a bit more, and it's given liquid level is 4 liters here. So this is containing 4 liters of liquid again at 110 degrees Celsius. Okay, means can I say that these two liquids are at same condition at 110 degrees Celsius and 110 degrees Celsius. Next, the remaining space in both the cookers is filled with saturated water vapor in equilibrium with the liquid water. So definitely this vapor is in equilibrium with this water. So that means this vapor is also at 110 degrees Celsius, which means there is some phase equilibrium between this vapor and liquid. Similarly is the case here. So here we have 2 liters of vapor, 2 liters of vapor. Okay, so total they have 6 liters, and of course this is vapor, of course it's of 4 liters. So this is the configuration of both the cookers. Now what they are asking you for, if G, small g represents the specific Gibbs free energy and the subscripts V and L represent the saturated vapor and the saturated liquid phases respectively, which of the following expressions is correct? So one thing, whenever phase change is happening, you know your specific Gibbs free energy remains constant, correct? Why? Because see here, you know your G is equal to H minus Ts, correct? And you know if you differentiate this, means to identify the change in Gibbs free energy, then you have dH minus derivative of T times of S. Of course the smallest that denotes your specific entropy as well. Okay, so dH minus differentiation of this is T times of ds minus S times of dt, correct? This is what we have. And you know dH minus TDS, we have the TDS equation. TDS is equal to dH minus VdP. That means you can write clearly that this dH minus TDS is equal to VdP. This is what we can write here, correct? So dH minus TDS is equal to VdP, and exactly that's the combination you have here. So in place of dH minus TdP, you can just replace VdP minus S dt. But one common thing that we know of a pure substance is whenever any pure substance is undergoing phase change, its pressure and temperature remains constant. So whenever your temperature and pressure is constant, means this dP is 0, similarly this dt is 0, so the total expression is 0, which means that implies G is equal to constant throughout the phase change, correct? So whenever here this liquid water and vapor are in equilibrium at 110 degrees Celsius, then definitely there is some equilibrium of this situation, and which means the Gibbs free energy of this vapor at A and this Gibbs free energy of this liquid at A, both are same. So we have one thing, Gibbs free energy of the liquid in state A is same as Gibbs free energy of vapor at state A. Similarly, in this case, if you have the same temperature of 110 degrees Celsius, then the properties of liquid which are here will be same as here, and the properties of vapor which are here will be same as vapor here. But since these two are equal, similarly we have G liquid of B is equal to Gibbs free energy of the vapor in situation B. And since you know this GLA and GLB are equal, which means one thing is very clear, all the 4 quantities are equal. Clear? So if all the 4 quantities are equal, then you can write G vapor at state A is equal to Gibbs free energy of the liquid in state B. So this option D is correct, and you know since all 4 are equal, we can say these 2 are equal anyhow. Look, you may write this option, but they are not asking you for the total Gibbs energy. They are asking you for the specific Gibbs energy. So even though some volume is double or mass is doubled and all, but of course mass is doubled in the case because density remains constant for liquids actually. So that's why I'm telling you. So this option is wrong because they are asking about specific quantities. Okay, they are not asking about total Gibbs free energy, but they are asking about specific Gibbs free energy. Let's go for the next question quickly. Okay, so this is one question we have. A frictionless piston cylinder device contains 1 kg of an ideal gas. So one thing that's clearly given here, the gas is ideal gas. Next, what's the mass of the gas that's available? 1 kg, and P V power 1 point, and the ideal gas is compressed according to the relation P V power 1.3 is equal to constant. Correct? So this is the relation that's given to us. So generally if you take the expansion or any compression PV per N is equal to constant, then we know, of course, if the ideal gas is having the ratio of specific heats as gamma, then in that case the net heat transfer is equal to gamma minus N divided by gamma minus 1 into mass times characteristic gas constant into T2 minus T1 divided by N minus 1. This is the formulation that we have. Of course, it's a standard formulation. It's nothing big. Actually, if PV per N is equal to constant, you can identify what is the work done, and if you can identify what is the change in internal energy, then the net summation of work done plus internal energy gives you this formula. Okay, so here it's given. Let us fetch some data from this. Okay, so let us fetch some data. PV per 1.3 is equal to constant, which means your N value is 1.3 and your mass is 1 kg. Next, so we got your N, we got our mass. And what about gamma? The characteristic gas constant is 287 joule per kg Kelvin and the ratio of specific heat capacities is 1.4. So it's clearly given the ratio of specific heat capacities is 1.4, which means you got your gamma. So what is gamma? Gamma is equal to 1.4. This is something that we know. Next, small or capital R, characteristic gas constant. This is equal to 287 joule per kg Kelvin. But finally they are asking in kilojoules. So let us write this, R in kilojoule per kg Kelvin. So 0.287 kilojoule per kg Kelvin. This is what we have. Next, so we got what is R. We need to know what are the initial and final temperatures. So here you can see here from 100 kilopascals to 50 Kelvin. So initially the temperature is 250 Kelvin. And what about final temperature? This is compressed till it reaches a temperature of 500 Kelvin. So you can see clearly this final temperature is also given, and during compression of an ideal gas the temperature increases. This is a common experience. Have you ever pumped your cycle air pump? So by the time you start pumping your air into the cycle, after some time you feel the hotness of the pump, correct? Which means the temperature of the gas inside the pump increases, correct? It's obvious, it's a common experience that every one of us feel here. So whenever you're trying to pump some air into the cycle type, then definitely the pump gets heated up after some time, because compressions, they generally increase the temperatures of the substance. Okay, so this is, we can see T2 is equal to 500 Kelvin. Okay, so that means we got enough data. We know what is N, we know what is T2, and we know what is T1. Everything is given in the question. It's only thing, just you need to substitute here and get the values. Let us get what is the value going to be. So Q is equal to gamma 1.4 minus 1.3 divided by 1.4 minus 1 into M. Mass is given, which is 1 kg. Characteristic gas constant is also given, which is 0.287. And T2 minus T1 is of course 250. Then 250. Then we have one more thing, which is N minus 1, which is, okay, since we have taken T2 minus T1, let us write 1 minus N here. So no issue. 1 minus N, since we have written T2 minus T1, so which is 1 minus 1.3. So if you calculate carefully, this is 0.1 and this is 0.4. So this is 1 by 4 totally. So this total value is nothing but 0.25. 0.25, because this is 0.1 and this is 0.4. So it can be written as 1 by 4 straight away. And this is 1 into, of course, 0.287 into 250 divided by minus 0.3. Minus 0.3. This is what we have. So let us calculate this value quickly using a virtual calculator. 0.25 into 0.287 into 250. So this is what we have, 17.9375. But of course there is a division to this, which is by minus 0.3. So minus 0.3. This is what we have. So minus 59.79 is what we are getting. So minus 59.79 kilojoules, of course. So this is what we have finally. And since they are asking you what is the heat transfer from the piston cylinder device to its surrounding. So here we got a negative value because it's obvious, doing your compression some heat gets out to the surroundings from the system. So that's the reason why we got a minus n here. But since they have already asked the question like the heat transfer from the system or the piston cylinder device to its surroundings, so they are already talking about loss. So it's just enough if we enter the numerical value here, which is 59.79 around. Okay, so 59.79 kilojoules is the exact value of the heat transfer that's happening in this process of compression. Okay, clear? So shall we go for the next question? All of you whoever is on live, so please respond. Shall we go for the next question? I hope things are very much clear. The only thing is, if you know a bit of formulas, you need to identify what are the values of exact terms in that. Clear? Okay, so let me go for the next question then. Let us go for the next question. So we have a thing, a closed system consists of a solution of liquid water and ethanol. And what is ethanol? Generally the ethyl alcohol that people consume, correct? So we know this. So a closed system consists of a solution of liquid water and ethanol in equilibrium. So now, if you could see clearly, there are two components. What are they? Number of components is equal to 2. And what are the two components? We have this liquid water here, and also we have this ethanol here. And it's clearly given both of these things are in equilibrium because they mix together and also they are in equilibrium. So with its vapors. So one thing we need to identify here, this liquid water is in equilibrium with the vapors of ethanol, correct? So please tell me, if liquid water and vapors of ethanol are in equilibrium, then total how many phases are present inside the closed system? You can go for the previous question also of this vapors question. So you can see here, liquid is in equilibrium with this vapor. So total how many phases are there within this closed system? How many phases are there within this closed system? Please respond. So how many phases are there within this closed system whenever this liquid is in equilibrium with this vapor? There are 2 phases, correct? So there are 2 phases. So number of components is equal to 2 and number of phases is also 2. So if you try to write the degrees of freedom, yes, correct, Abraham. And Dharmendra, sorry, we didn't find the question actually from the sources. So I thought of giving the solution for that, but of course we'll be later posting that solution alone, I mean single solution of that question. Okay, better. So now see here, number of phases is equal to 2. So now one thing we can get, so degrees of freedom they are asking you for. So degrees of freedom F is equal to C minus P plus 2. And what is this rule called? This is the Gibbs phase rule. This is the Gibbs phase rule. Okay, so this implies F is equal to your number of components is 2 minus number of phases is 2, so plus 2. You know this plus 2 and minus 2 gets cancelled, so this is 2. So number of degrees of freedom of this particular substance in this situation is 2. So the answer is 2, which is in the 4th option. Clear? Because see, whenever you are having some mixture of 2 components in 2 different phases, it's always known to us we need at least 2 independent properties or exactly 2 independent intensive properties to define the state of the system. And that's why you can see clearly the degrees of freedom is also 2 when evaluated using Gibbs phase rule. Clear? Let's go for the next question. So this is a very simple question. It's again depends on Maxwell relations. Just now we have solved. If V is the mass specific volume, S is the mass specific entropy, and P is the pressure, T is the temperature, then using Maxwell relations, what could be the value of dou S by dou P at T? So this, we know this. You know, Gibbs free energy G is equal to H minus Ts, which I am doing in the beginning of the class today. So see here, if you look at this complete analysis, if you stop at this point, then you have your dG is equal to V dP minus S dt, correct? This is what we have. Let us write this equation, V dP minus S dt. So dG implies V dP minus S dt. And you know, Gibbs free energy is a property of the system, correct? It's a property of the system. So whenever these are properties, they are point functions, means they are exact differentials. So if this has to be an exact differential, you know clearly in mathematics we have a relation dz is equal to m dx plus n dy. If this is of this form where m and n both are functions of x comma y, then you know dou m by dou y at constant x, this should be equal to dou n by dou x at constant y. This is what we can hear. And if this G is an exact property, then that if you compare these two equations, one thing that you should have, dou V by dou T at constant pressure, this should be equal to dou of minus S divided by dou P at constant temperature, which is equal to minus dou S by dou P at constant temperature. So dou V by dou T at constant pressure is minus dou S by dou P at constant temperature. So one thing that you can conclude, dou S by dou P at constant temperature will be nothing but negative of this particular value, which is minus dou V by dou T at constant pressure. Clear? So this is what we have. And that's what they are exactly asking you in question. What is the value of dou S by dou P at T? So dou S by dou P at T is equal to minus dou V by dou T at P, which you can see clearly in this third option. Minus dou V by dou T at P is given in the third option. So this is the correct answer. Clear? I hope you can understand the things. Okay, so this is the correct answer because it's a simple Maxwell relation that you can easily derive at any point of time. Because you know, if this Z is a property, then definitely this is the condition for exactness of the differential equation, and here this is a differential equation. Yes, correct, Aman. 3 is the correct answer. Next, let us try to solve this. A mixture of air and water vapor enters a steady flow adiabatic saturator at 50 degrees Celsius and 100 kilopascals. Okay, so let us try to frame the diagram. Look, there is one adiabatic saturator. What is the meaning of this adiabatic saturator? Look, let us try to use some things here. So this is one adiabatic saturator for the time being. Okay, so now, okay, so let us try to read the question. Adiabatic saturator, a mixture of air and water vapors, which is generally the moist air. Okay, so some moist air is entering this steady flow adiabatic saturator at 50 degrees Celsius and 100 kilopascals. So now if you see, this is adiabatic saturator. So this is your adiabatic saturator, which means there can't be any heat interactions. There can't be any heat interactions. So some air, moist air is entering here at 50 degrees Celsius. So this is 50 degrees Celsius and P is equal to 100 kilopascals, or P1 is equal to 100 kilopascals. Then what's happening to the next? Look, it leaves the saturator in a completely saturated state at temperature of 25 degrees Celsius and pressure of 100 kilopascals. From this statement, we can identify 3 important things. The liquid leaves, or the moist air leaves the saturator in a completely saturated state at temperature of 25 degrees Celsius and pressure of 100 kilopascals. These are the 3 important numerical data that we can obtain from this particular statement, that the air is completely saturated. What's the meaning of completely saturated? Here the relative humidity is 100%. Correct? Next, temperature is 25 degrees Celsius. Okay, and pressure is again P2. This is same, which is 100 kilopascals. Correct? So next, let us read the question. Liquid water enters the saturator at 25 degrees Celsius. Of course, how saturation occurs? There will be some liquid water, some feed water, or some backup water which is situated here, which enters through some inlet, of course, and it forms some layer which has some good enough length, so that by the time your air reaches this point, it is completely saturated. Okay, so I am trying to draw some air molecules here. So what does this air molecules do? They try to take some water vapor along with them, and this adiabatic saturator is good enough, or it's of some finite length, such that the air gets saturated by the end. Okay, so there will be some water leaving from this water to air throughout the path, and of course by the time it reaches this, it goes to Paitala Nagaraju. Speak slowly in sense like number of words less per minute or less tone. Anyhow, I hope you have the volume buttons in your hand and even this play speed in your hand, so you can adjust accordingly. Clear? Look, so now this is the situation. So what they are asking you for now? Liquid water enters the saturator at 25 degrees Celsius. So this is 25 degrees Celsius, and generally we maintain the backup water also at 25 degrees Celsius. Because can you tell me what happens if this is not 25? Can you tell me what happens if this is not 25? Generally we maintain that both these temperatures will be same in general. Because if this is of some higher temperature or some lower temperature, then there will be some heat transfer between these two substances. Okay, but since this being an adiabatic saturator, there should not be any heat interaction that should happen, and definitely both these things have to be at the same temperature. Okay, next, if air is considered to be an ideal gas, of course we do that with constant specific heat capacity, the relative humidity of air entering the saturator. So you can see here they are asking you what is your phi 1, relative humidity at inlet. This is what they are asking you for. Now how we can calculate phi 1? Look, first of all, if we have enough analysis on what is specific humidity, then definitely we come to know what is relative humidity. Correct? This is known to us. So what is the expression for specific humidity? 0.622 PV divided by total pressure minus PV. Of course, we derive this in our thermodynamics classes, but of course, for time being, we just take this. Aman Singh, I would like to tell one thing for you. Sir, XC65, any chance in IITs? One fact that I would like to display here, till last year, till 2020, the number of candidates writing XC were around 3,700 and 3,800, somewhere in between that. But this time, since the IIT Bombay has provided the opportunity to write 2 papers, it's almost got 10 times of that. Okay, so around 36,000 students have given XE in this year. So depending on the marks and the competition, till the final result is out, we don't have any general expectations that such marks or some score could be enough to go into IITs. Okay, because compared to the ordinary core subjects like core papers like mechanical or civil, the number of seats that are offered to the XE aspirants is low a bit. Okay, so but of course please don't get discouraged, because final keys are yet to out, final answers are yet to out, and definitely you'll find some good chance. Okay, so be strong, Aman. Next, so this is the iteration for omega. Now one thing is very clear, again phi is nothing but PV divided by P saturated at that same condition. So this is the relation. Now if you consider this case exit condition, your phi is 100%. Yes and why? How many gave instrumentation? No idea, but of course I think decently a good number, because all ECE and typically all other combinations can write instrumentation. Okay, so let us wait peacefully for the final display. But the only information that IIT Bombay displayed as of now is only there was 78% attendance in the gate. Okay, so there is only 78% of attendance. So which means out of every 100, only 78 people wrote the exam in general. Okay, so this IIT Bombay has given officially. Next, so let us quickly go to this question. So if phi is equal to 100%, which means at state 2, your PV at state 2, this is same as P saturated PV saturated at state 2, and this is given to us. This PV2 is equal to, how much is this? So it's clearly given at 25 degrees Celsius, your P saturation pressure is 3.161 kilopascals. So which means here the value is 3.161 kilopascals. So from this we can calculate omega. Okay, so omega 2 is equal to, we know this expression 0.622 into PV divided by P total minus PV. So 0.622 into 3.161 divided by, we know the total pressure at the exit is given 100 kilopascals. So 100 minus 3.161. This is what we have, and this implies omega 2 is equal to, let us calculate this value, 0.622 into 3.161. So 3.161 divided by 100 minus 3.161. So this is what we have, and 0.0203 is the value that is with us. So let us write 0.0203 kg of vapor per kg of dry air. Per kg of dry air. This is nothing but omega. So omega is known. So if you can identify what is the amount of water that's being added in this case, we could easily get what is phi 1, and of course we'll get what is omega 1. Correct? Now let us apply the energy balance. The energy, that the amount of water vapor will be very small. So let us apply the energy balance for the system throughout. So at point 1 or at section 1, let us write the enthalpy. At section 2, let us write the enthalpy, and let us write the enthalpy of evaporation also here. Okay, so now omega 1 is nothing but some kg of vapor per kg of dry air, and omega 2 is some again kg of vapor per kg of dry air, and in between we are not supplying any air into the chamber. So which means the difference between omega 2 and omega 1 will be the mass of this water which is getting evaporated. Will you agree with me? Yes or no? Look, we are not supplying any air to this chamber. If this chamber is not being supplied with air, then whatever the difference between the water vapor here and at this point, the difference between these 2 points is nothing but the mass of the water that's getting evaporated in the saturator. Yes or no? Is that clear? So now, if that's clear, look here. Let us write the energy balance. So energy balance is nothing but H1 plus omega 2 minus omega 1, because this is the mass of the water per kg of dry air that's getting evaporated, into the enthalpy at this point, since this is liquid water. So HF at, since this is at 25 degrees Celsius, this is at 25 degrees Celsius, this is equal to H2. So this is the energy balance. Now what does the specific enthalpy of this mixture contains? It contains the enthalpy of air plus enthalpy of water vapor. Correct? So let us write this as 1.005, or this, because the specific heat of air is given clearly. You can see here the specific heat capacity of air at constant pressure, Cp is equal to 1.005 kilojoule per kg Kelvin. So let us write this as 1.005 times, since this initially the air is at 50 degrees Celsius, let us write this 50 degrees Celsius plus, now what about enthalpy of water vapor, which is omega 1, because water vapor is omega 1 grams per kg of dry air. So omega 1 into, so depending on the wet bulb temperatures, you can see clearly this 50 degrees Celsius Hg can be taken as the enthalpy of the moist air here or water vapor here. So 2592.06. 2592.06. This is what we have here, plus omega 2 minus omega 1. Omega 2 minus omega 1 into HF at 25 degrees Celsius. So you can see, since the water is at 25 degrees Celsius, the enthalpy of the liquid phase of water at 25 degrees Celsius is 104.87. So let us write this as 104.87 is equal to, again, enthalpy at state 2, which is 1.005 into 25 plus omega 2 into enthalpy of water vapor, again at this dry bulb temperature or this wet bulb temperature, can be taken as, which is 2547.17. So 2547.17. Correct? So this is the expression, and of course from this, if we can find omega 1 from this one equation, then definitely we can calculate what is phi 1. So let us calculate. Let us see what are the things that we know. Omega 2 is known to us, which is 0.0203. Here also we know omega 2, which is 0.0203. Then this is only a single variable equation, which is omega 1. So let us try to calculate omega 1 from this equation. So to calculate omega 1, you can cancel these terms, and this 50 becomes 25 here, because 25 times into 1.005 will get subtracted from this 50 times of 1.005. So this omega 1 is equal to, this right hand side we have the value 0.0203 into, so 0.0203 into, what do we have there? 2547.17. 2547.17. This is the value, 51.707. Okay, next, minus. We can do one thing, we can subtract 0.0203 into 104.87. So minus 0.0203 into, what's the value? 104.87 into 104.87. So this is the value that you can subtract directly, and of course, now we can also subtract this value minus 25 times of 1.005. So minus 25 times of 1.005. This we can subtract. So 24.45369 is available with us. So 25.45369 divided by 2592.06 minus 104.87. So this value is your omega 1. So let us calculate what is this value. So if this is our value, 25.45369 divided by 2592.06. 2592.06 minus 104.87. 104.87. So this is what we have, and omega 1 is nothing but 0.0098. So your omega 1 here is nothing but 0.0098 kg of vapor per kg of dry air. Kg of dry air. So omega 1 is known to us. So if omega 1 is known to us, then what can we write? Omega 1 is equal to, again, omega 1 is equal to 0.622 vapor pressure of water at state 1 divided by P minus PV1 at state 1. So this implies your omega 1, which is 0.0098 divided by 0.622 is equal to, this is 100. So PV at state 1 divided by 100 minus PV1. This is what we can write. So definitely if you calculate this value divided by 0.622. So this is the value of this. If you invert this, 100 by PV minus 1 will be equal to the reciprocal of this, which is 0.622 divided by 0.0098. So this is something that we have. So the reciprocal of this value plus 1, which is 64.26375 is here. So this implies 100 by PV1 is equal to something around 64.2637. 64.2637. So if you calculate what is the vapor pressure at state 1, PV1 is equal to 100 divided by this value. So 1 by x into 100. So this is 1.556. 1.556 kilopascals. So this is the pressure at this. This is the pressure of vapor at this situation. So if you want phi 1, it's very simple. Phi 1 is equal to 1.556 kilopascals divided by, what is the saturation pressure value that's given? at the initial conditions at 50 degrees Celsius, your saturation pressure is 12.335. So if you write this 12.335, let us calculate this value. What could be this value? 12.335 divided by 12.335. So you can see 0.1261. So 0.1261. But of course, I think they are asking you in percentage. So yes, they have put a percentage symbol here. So 100 times of this, which is equal to 12.61 percentage. Okay. So 5.1 is equal to 12.61 percentage. This is the only lengthiest question of the paper. And of course, it's not actually lengthy, but it appears to be lengthy because you can see clearly this is a one equation, one unknown. Okay. So you need to solve that. But of course, solving this equation need to be done a bit carefully. Otherwise, your values of omega 1 changes. Okay. And one thing I am telling you, why I have calculated omega 2 in the beginning, because you know clearly in a saturator, definitely this omega 2 will be more than this omega 1 because some water is being added to the air. Correct. So once you have omega 2, you have two advantages. One thing, you can solve this equation obviously, and one thing, when you get this value, definitely the value which you get here should be definitely less than this, because amount of water that's present at this point will be definitely less than amount of water that's present at this point. Correct. So there are two benefits of calculating this omega 2 here. Okay. And of course, without omega 2, we can't go ahead in this equation. Yes. So this is the only question that's a bit appears to be a bit lengthy in this paper, but of course, even that can be solved very easily. Clear? So now let us move forward. For a real gas passing through an insulated throttling valve, the outer temperature of the gas dash with respect to the inlet temperature. Many of you might have marked remains same, but it's actually not, because one thing, it's clearly mentioned for a real gas and it's exactly 0 only for ideal gas case, because you know something called, there is something like Joule-Thomson coefficient, correct, which is denoted by mu. And what does this Joule-Thomson coefficient do? This is nothing but dou T by dou P for constant enthalpy process and at constant H. Will 13.157 be accepted? And the difference between 12.6 and 13.1 is around 0.5. But of course, when this is 12.6, I think the range could be somewhere around 3% to the right and left of this. So 10% of this is 1.2. So 3% could be something around 0.3 something like. So 12.32, maybe 12.9 or at max 13. Okay. So I think 13.15 is a bit out of the domain Herschel. But of course, again, the IITs take all these things into consideration. So there is a probability still that this 13.157 will be in the range. Okay. Because you know all these calculations are very small, like 0.0203, 0.0098. So of course it's quite possible when you round off the things, you get such answers. So I feel like IITs generally, if you look at the past year answer keys and all, they take this into consideration. Okay. So no issues. Anyhow, let us try to solve this question. So there is something like this, correct? So what is throttling? In throttling, you know the initial enthalpy and the final enthalpy is same, or in general you can say that the change in enthalpy is 0, because if you apply the steady flow energy equation for a small throttling device, so this is your throttling device, you know you generally throttle. So generally if this is your small throttling device, you know if you write your steady flow energy equation, Q dot minus W dot is equal to delta KE plus delta PE dot plus delta H dot. This is your steady flow energy equation. Now this implies this process of throttling means if you allow some gas to pass through this, definitely that undergoes a constant enthalpy. Because why? Look, we gonna assume some terms to be 0 and we'll assume that those terms to be 0. Why? This Q dot is 0. Why? Because you know heat transfer can be associated as heat transfer rate into time, correct? So if this is happening, if this Q has to be 0, then two things can happen. One thing that this Q dot can be very small, and one thing this T can be very small. And you know, whenever throttling device is very small, you know, throttling device is of just some centimeters. So whenever fluid is passing at some velocity, the time that this throttling, the fluid will be in contact with this throttling device will be very small. And in that small time, it's really difficult for some heat to interact with the fluid. Many of us will play at the home in the kitchen, correct? There will be some hot cooker and we'll be trying to touch the cooker and take the hand quickly. You know the cooker temperature is so high, but we don't get hurt because the time of contact between your hand and cooker is very small, so that you can't get any heat transfer. Okay, same is the situation here. Since the time of interaction of this fluid with this throttling valve is very small, the heat transfer is almost negligible. Similar is the W dot, because you can't see any displacement work or flow work here. And of course, you know, for mechanical increase in its energy, means if for any kinetic change in its energy, it needs some time, correct? So, but throttling device is very small again, such that there won't be any considerable changes in velocities, which means the kinetic energies or the bulk kinetic energies of the fluid remains same at inlet and outlet. Similarly, whenever this valve is very small, the potential differences or the datum differences are very less, so you can also equate this term to 0. So that's how you can face this throttling as an isenthalpic process. Finally, this delta H is equal to 0. This is how you will get throttling. Sometimes you call this as isenthalpic process because your final enthalpy and initial enthalpy are same, and the change in enthalpy is 0 generally. Okay, so this delta H is equal to 0. Now, if this is an ideal gas, for ideal gas, obviously your enthalpy is function of temperature alone, and of course, if delta H is equal to 0, that means this implies your delta T is equal to 0, which means your temperature remains same. But of course, this is the case only for ideal gas. But if for any real gas, for real gases, your enthalpy is a function of both temperature and pressure. Okay, so both temperature and pressure. And in throttling, temperature may remain same for ideal gas, but of course, in throttling, the general phenomena that occurs is there is some pressure drop. Correct? You have seen this refrigeration cycles. If I would like to draw some reverse cycle very soon, we see as in the pH plot. If you have a pH plot, something like this, then you could clearly sense if you try to draw the refrigeration cycle. So this is the cycle, correct? 1, 2, 3, 4. And you can see this is throttling, and throttling is irreversible because within that small path we don't know what is the exact path traced by the fluid, so definitely we will represent this with a dotted line because this process is irreversible. Now, if this is the case, this is your condenser pressure, and of course this is your evaporator pressure. So now during throttling there is some pressure drop, but again you see this is the space where you are taking heat from your phase. This is the location of your deep phase. You can see there is some temperature difference between this condenser and evaporator, correct? Normally if you touch condenser you feel a bit hot, but of course here you have evaporator again, which is very close to your deep phase. So now here you can see one thing, there is some temperature drop, correct? During throttling, along with pressure drop, there is also some temperature drop of the fluid, which means there is some ratio. So this mu can be greater than 0, or for few fluids this mu can be less than 0 as well. And for ideal gas, this mu, which is the change of temperature with respect to pressure drop, is 0. And for refrigerant, whenever there is pressure drop, there should be temperature drop as well. So this mu has to be greater than 0 for refrigerants. Okay. So depending on this, Joule-Thomson coefficient, we decide whether during throttling a substance will increase its temperature or decrease its temperature, or it may remain same. So generally, this 4 is the correct answer. This is valid. Is always same, is valid only if there is ideal gas here, but in the rest of the cases it need not be equal. Clear? I hope you are getting the things. So let's go for the next question quickly. So a 0.8 meter cube insulated rigid tank contains 1.5 kg of an ideal gas at 100 kilopascal. So there is one rigid tank. What is the meaning of rigid? This is rigid, which means your volume is constant. Next, volume is constant. And of course, this tank is insulated. This tank is insulated. So now, what is being done? This is insulated. So tank is insulated, which means no heat can be exchanged from surroundings to the tank or from tank to the surroundings. Next. So this tank is of volume 0.8 meter cube and it consists of 1.5 kg of ideal gas. Okay. At 100 kilopascals, of course. So P1 initially this is 100 kilopascals. Now, what is done? Electric work is done on the system until the pressure is the tank rises to 135 kilopascals. So electrically some work is done. So what can be done? Electrical work. Some electrical work is done inside this. So let us suppose there is some resistor, and if this is your system, then you can say some electrical work is causing your system. So finally, because of the heat generated internally, definitely there will be some pressure rise, and it's clearly given your pressure rise P2 is equal to 135 kilopascals. 135 kilopascals. Next, the lock-in availability or exergy of the system associated in this process in kilojoules, of course. So they are asking you for loss-in availability, so which means irreversibility. Correct? This is equal to T naught into delta S of universe. Correct? As per Gauss-Todolo theorems. So now if this irreversibility is equal to T naught, which is where this T naught is the ambient temperature, that could also be given. Yeah, the temperature of the dead state is 298 Kelvin. So this T naught is 298 Kelvin. So definitely if this is your 298 Kelvin, one thing that you need to identify, what is the change of the entropy of the universe for this process to happen. Now if you want to identify what is the change in entropy of the universe, then delta S of universe is nothing but delta S of system plus delta S of surroundings. But here in this case, I write this delta S of surroundings has to be 0 because this system is insulated. Correct? And entropy change is associated only with heat transfers but not work interactions, because work is always an organized form of motion. Correct? So definitely whenever there is some heat in insulation around the tank, then definitely there can't be any entropy change of your surroundings. So the only thing is this can be written as T naught into delta S of system in this case. And how you can identify the delta S of system? Since entropy is a property of the system, so either the process happens by a reversible way or an irreversible path, definitely the entropy changes are same. Correct? So this implies irreversibility is equal to T naught, which is 298. Let us write the values. 298 into change in entropy of the system, which is mass, which is 1.5 kgs. So 1.5 into change in specific entropy. Now a change in specific entropy can be written as Cp ln T2 by T1 minus R ln P2 by P1, or if you write in terms of volumes, we can have Cp, which is given here, Cv, yeah, capacity of constant volume, which is 680 joules per kg Kelvin, but here the answer is in kilojoules, so let us write this in kilojoules. 0.680 into ln P2 by P1, which is 135 divided by 100. So this is the value that is with us finally. So irreversibility is equal to, let us calculate this value. That's the value that we have. So 1.5 into 0.680, 1.5 into 0.680 into ln of 135 by 100. That's 1.35. So let us write into 1.35 ln and into, we have some more thing, which is 298 to multiply. So 298. If you multiply all these things, so 91.219 is the kilojoules of XHG that's getting destroyed. So 91.219 kilojoules, of course, because we have substituted the Cv in kilojoules. So irreversibility of the system is equal to 91.219. 91.219. Okay. Next, let's go for the next question. This is the easiest question. So atmospheric air with a divergent temperature of 24 degrees Celsius. So one thing has to be done. This data can be identified. And a relative humidity of 35%. So there is a relative humidity of 35%. Okay. Entering in a circular duct, assume no pressure drop in the duct. Okay, so basically some moist air is entering a circular duct and there is no pressure drop in that duct. Is heated by a electrical resistance arrangement inside the duct. So basically there is some circular duct and there is some inflow of moist air. And what they are doing? They are heating this air with the help of some electrical resistance arrangement. So definitely this air, after taking some heat, it again comes here. Okay. So no water is added. So which means this can be treated as a case of sensible heating. Okay. Because there is no increase in the humidification levels. So because no water is being interacting at this point, so only some heat is flowing in. Then electrical resistance arrangement inside the duct. The dye temperature of air measured at the outlet of the duct is equal to 30 degrees Celsius. Obviously, because there is no water vapor that is going in, but because of this heat supplied by this resistor at this point, the temperature, if this is T1 degrees Celsius and if this is T2 degrees Celsius, then definitely your T2 has to be greater than T1 because of this heating. And it's quite obvious, you can see this is 24 degrees Celsius and this is 30 degrees Celsius. Okay. Next, considering the flow to be steady, which of the following statements is or are correct? And this is the only question in MSQs that came in thermodynamics this year. Okay, so this is a multiple select question, so there are more than one answers. So if you take that psychometric chart in general, so if you take the psychometric chart, let me take the help of these lines. Okay, so anyhow, let us try to draw a neat line. Okay, and let us try to have this omega also. So if this is your small diagram that's available here. Next, so you could see here the psychometric chart looks something like, let me draw. Okay, and let me try to draw this one more time. Okay, so now we have a connection with a smooth curve. Let us draw that. Okay, so this is how your psychrometric chart looks. Now, this is your dye bulb temperature in degrees Celsius, of course, and this is the axis of your omega, which is specific humidity, kg of vapor per kg of dye air. This is what that's available with us. Okay, so now let us put a big arrow, and similarly here. Okay, now you know this is your phi is equal to 100% line, and normally if you try to draw other lines then in this chart, so you know if this is your phi 1 is equal to constant, and similarly if this is your phi 2 is equal to constant, so let us suppose this is your phi 2 is equal to constant. Now there is some sensible heating, correct? So during sensible heating, it's obvious your temperature increases, but your specific humidity doesn't change, correct? Because there is no water vapor that's being added to the system. So without changing any omega, your temperature increases. This is known to us, correct? So from 1 to 2, this is the state. And you know the dye bulb temperature, the wet bulb temperature, what are they? Dew point temperatures, So the dew point temperature lines will also look similar. Let us try to draw. The dew point temperature lines also look something like this, correct? So these are your dew point temperature lines. Now, if this is sensible heating, one thing that we can tell here, this is omega is equal to, phi is equal to phi 1, and this is phi is equal to phi 2. So one thing that you can tell, phi 2 is less than phi 1. So your relative humidity doesn't remain the same. But you can see there is no change in omega. So your omega remains same, and of course your dew point temperature also remains same. But your dye bulb temperature doesn't remain same again, correct? So if you go for the options once, there is no change in the relative humidity. No, this is wrong, because you see that the relative humidity decreases actually. Next, there is no change in the dew point temperatures. Yes, this is correct, because dew point temperature lines are parallel to the dye bulb temperature lines, and of course their dew point temperature doesn't increase in general. So there is no change in the specific humidity. So there is no change in the specific humidity. Yes, this is also correct, because there is no addition of water vapor into the system. So definitely omega remains constant. Next, there is no change in the specific enthalpy. No, enthalpy increases, because you know the temperature of the air content increasing. So this is atmospheric air. So in atmospheric air you have dry air and plus moist vapor, correct? And the enthalpies of both these things increases with temperature. So definitely there is some increase in specific enthalpy also. So this is wrong. So only 2 and 3 are correct statements in this case. Okay. So 2 or 3 are the correct statements. So if you want to get marks for this question, definitely you could opt only 2 and 3, not any excess or not any short of this. Okay. This is the easiest question, of course. Just if you have basic idea on psychrometric chart, that can be solved. Next, there is one question. For the efficient R134 at 1 megapascals and 50 degrees Celsius, so it's given, some properties of the substances are given here. Pressure is equal to 1 megapascal, which means 1000 kilopascals. And temperature is equal to 50 degrees Celsius, which means 323 Kelvin. Of course, 323.15 to be more accurate, but of course, 0.15 is very small compared to 323, so I am neglecting. The difference between the specific volume computed by assuming it to be an ideal gas and its actual specific volume is V ideal minus V actual. Okay, so the V ideal is the specific volume that's evaluated using ideal gas equation, and of course this is the actual volume, of course specific. The difference between these two things is 4.529 into 10 power minus 3. Of course, since they are specific volumes, the units are meter cube per kg. Next, if the compressibility factor associated with the state is Z is equal to 0.84. So compressibility factor is equal to 0.84. And if the compressibility factor associated is Z 0.84, then V COM minus V actual. So where V COM is the specific volume calculated using the compressibility factor. Okay. So we know this compressibility factor is equal to 0.84, which is nothing but V computed using compressibility factor divided by V ideal. Correct? This is something that we know. Now, if you know this, they are asking you for V evaluated using compressibility factor minus V actual. So they are asking you for this difference. So let us write. This implies V compressibility factor used is equal to 0.84 times of V ideal. 0.84 times of V ideal. So one thing is very clear, V computed using compressibility factor is 0.84 times of V ideal. Now they are asking you for V computed minus V ideal, correct? V ideal or V actual? I think they are asking you for V actual. Okay, fine. This is V actual. This is the value that they need. Now what we can do? V com minus, look, we know the relation between V ideal minus V actual, correct? So here what we'll do, we'll subtract one V ideal and we'll add one V ideal minus V actual, of course, because you know you can cancel these two terms at the end. So if you can cancel these two terms, again this ratio is same as this, and V compressibility factor is nothing but 0.84 times of V ideal minus V ideal plus V ideal minus V actual is already given, which is this value. V ideal minus V actual is already given, which is 4.529 into 10 power minus 3. So 4.529 into 10 power minus 3. This is the value that is with us. So this is equal to 0.84 minus 1, which is minus 0.16 into V ideal. You know PV is equal to RT. PV is equal to RT. So your V is equal to RT divided by P. And here this is in meter cube per kg. So definitely we'll go for R in joules. Okay, so this is 0.0815, and of course this is in kilojoules, and T is here, so pressure will substitute again in kilopascals. So let us do that. R 0.0815 into temperature is 323 divided by, divided by, then your pressure is 1 megapascals, which is 10 cube, plus 4.529 into 10 power minus 3. So let us take 10 power minus 3 common from all the things. So if you take 10 power minus 3 common, this also into 10 power minus 3. So we have 4.529 minus 0.16 into 0.0815 into 323. This is what available with us, correct? So let us calculate this value, and the value which is in the brackets here, in this flower brackets, that's the answer, because in the answer they have already mentioned this 10 power minus 3 here. So let us calculate what is the term that's in the brackets here. So 4.529 minus 0.16 into 0.0815. 0.16 into 0.0815 into 323 is the temperature in Kelvin. So if you see the difference, 0.317 is the answer. So we can go and we can write this difference as 0.317 into 10 power minus 3 meter cube per kg. And here this difference is given as this quantity into 10 power minus 3. So the fill in the blank that best suits here is 0.317. Okay. So this is how we can solve this directly without actually finding what is the actual volume. Okay. Because if you want to find actual volume, again calculations get a bit increased, but of course there is no such necessity. We can directly go for this. So 0.317 is the correct answer. So we are done with 12 questions. We have 10 more questions. Let's go through them quickly. Next. Let us go for this question. The saturation pressure Psat of a pure liquid is represented by an equation of the state ln Psat is equal to A minus B by T. So one thing that we have here, ln of this P saturation is equal to A minus B by T. Okay, this is what we have. So they are asking you for where, of course, A and B are constants and T is the absolute temperature. For this substance, which of the following expressions are for specific entropy difference between the saturated vapor and the saturated liquid phase? SFG is correct. We know generally for saturated liquid states we denote with SF, and for saturated vapor states we denote with SG. So the difference between them is SFG. Okay. This they are talking means during phase change, what is the value of this change in entropy? Subscripts F and G refer to saturated liquid and saturated vapor phases, of course, and VFG is the specific volume difference between again saturated vapor and saturated liquid. Now we know one very famous equation, which is the Clapeyron equation, correct? What does Clapeyron equation tells us? dP by dt saturation means if there is some phase change, then the difference between dP by dt at two phases or at two phase change process, that is equal to HFG divided by T sat into VFG. This is known to us. Okay? This is the Clapeyron equation. So let us calculate what is dP by dt saturation, because we have the relation between P and T. So let us calculate. If you differentiate this with respect to T, we have 1 by P sat into the differentiation of this with respect to T, which is dP by dt, because we are dealing at saturation states only. So this is equal to differentiation of this with respect to T is differentiation of a constant is 0, and differentiation of this term minus B by T is B by T square. Correct? This is what we have. So they are asking you for SFG. Let us see one thing carefully here. What is this ratio of H by T during phase change? HFG is nothing but T sat into SFG, correct? Because you know TDS is equal to DH minus VDP. We know this, correct? And during the phase change process, this pressure remains constant for a pure substance, and this DH is nothing but TDS, which means this HFG we can write this as T saturation into SFG. So this implies dP by dt saturation is equal to HFG can be written as T saturation into SFG divided by T saturation into VFG. So they get cancelled, and of course SFG is VFG times this ratio. So which implies dP by dt sat is equal to B into P times of saturation divided by T square. This is the expression with us, and of course if you want SFG, then SFG is nothing but VFG into this value. So this value into VFG is nothing but SFG, correct? And that's we can see here, B into P sat into VFG. So B into P sat into VFG divided by T square, which is in this expression. So 2 is the correct answer in this case. Okay, so 2 is the correct answer, because yes, here you can see clearly this SFG is nothing but this VFG into this dP by dt saturation. So this dP by dt saturation is B times P sat by T square. So if you multiply this term with one VFG, you will get SFG here. Okay, so that's given in second option. Of course, this is asked for 2 marks, but of course this involves a bit of mathematical differentiations. That's it, nothing other than this. Clear? Next, let us go for the next question. So a rigid tank contains 1 kg of pure water consisting of liquid and vapor phases in equilibrium at 10 bar. So one thing is given, a rigid tank contains 1 kg of pure water. So total mass that's available is equal to 1 kg. And of course there are 2 phases in this. In equilibrium at 10 bar. So pressure is 10 bar. Okay. Now, if the liquid and vapor phases each occupies 1/2 of the volume of the tank. So there is some volume, and in this volume exactly half is occupied by liquid phase, and the other V by 2 is occupied by vapor phase. The other V by 2 is occupied by vapor phase. Now, each occupies 1/2 of the volume of the tank. Then the net enthalpy of the contents of the tank. So net enthalpy, of course, they are asking you in kilojoules, and of course the total mass is only 1 kg. So which means that's equal to the specific enthalpy, correct? So H is what we want. HF, you know, if H is what we want, then HF plus X into Hg minus HF, where of course this X is the dryness fraction. That's the value of specific enthalpy of the case. Okay, and in this case total enthalpy and specific enthalpy both are same, because the mass of the substance inside is 1 kg, correct? So if the mass is 1 kg, then this is the expression that you have for calculation of specific enthalpy, correct? So here one thing that we should know is, we know what is HF, we know what is Hg. The only thing that we know what should be this value of X. We have one technique for that. Look, mass of liquid phase. Can we write this as, according to my experience, Guru Singh, people means based on the analysis and all papers, both papers are moderate level, but of course in the morning slot, in the forenoon slot, paper was a bit, few logical questions were asked actually. Okay, so forenoon was told to be tough, not tough, relatively a bit harder when compared to other things. Okay, so mass of liquid, this can be written as, look, mass of the liquid into specific volume of the liquid. This can be written as total volume of the liquid, which is V by 2, correct? Next, if you consider the same case, mass of the vapor into specific volume of the vapor, this is equal to again V by 2, which is the total volume of the vapor, and that's exactly half. So one thing that we have here, mass of liquid into specific volume of liquid is equal to mass of vapor into specific volume of vapor. This is what we have. Now we can just readjust the terms to some extent. We can write mass of vapor divided by mass of liquid. This is equal to, or let us write mass of liquid divided by mass of vapor. This is equal to, if this mass of vapor comes to this side, then this VL goes down. So VV divided by VL. Now if you add 1 on both sides of this equation, then this implies mv plus ml, which is mass of vapor phase plus mass of liquid phase divided by mass of vapor. This is equal to Vv plus Vl divided by Vl, and this is nothing but 1 by dryness fraction. So this is 1 by dryness fraction, correct? Because you know dryness fraction is nothing but mass of vapor in the mixture divided by the total mass, but it's a reciprocal of that. So this is 1 by x, and this implies VV plus VL divided by VL. This is what we have. So let us substitute the values. What is VV that's available here? V, which is the specific volume of the vapor, which is 1. Since 10 power minus 3 is there, 0.194.3. So 0.194.3, right? 0.194.3. This is what we have. Next, plus Vf, which is 0.001127, 0.0011, 0.001127. This is what we have, divided by, in the expression what is there first, in the final expression we have VL in the denominator, correct? So VL is nothing but again 0.001127. This is 1 by x. So 1 by x is 0.0057 is the Dynamis fraction. So your Dynamis fraction is 0.0057. Okay, this is your Dynamis fraction. So we know HF and we know HFG. So let us calculate the values quickly. Let us calculate the values. So x is this. So H is equal to HF, which is HF is 762.7. I mean 762.6. So 762.6 plus x, which is 0.0057 into the difference between these two values, which is Hg minus HF. So 2776.2, 2776.2 minus HF value, which is 762.6. This is the value that you need to calculate. So if you calculate this value, we will be getting this into 2776.2, 2776.2 minus what do we have? 762.6, 762.6. So this is something that we have, plus HF is there. So 762.6 to be added. 762.6 has to be added. So 774.2 kilojoule per kg, or we can write this as 772.4 kilojoule per kg. But of course, since the total mass is 1 kg, we can write the enthalpy at the end is equal to 772.4 kilojoules. This is what we can write here. Okay, so 774.2 kilojoules is something that we can write as direct enthalpy value. Next, let us go for this question. For a refrigeration cycle, the ratio of actual COP to the COP of a reversible refrigerator operating between the same temperature limits is 0.8. So one thing that's clearly mentioned here. What's the thing that's clearly mentioned here? COP actual is to the COP of Carnot or reversible refrigerator. This is 0.8. Obviously, COP of this refrigerator will be more. That's known to us. The condenser and evaporator temperatures is 51 degrees Celsius and 30 degrees Celsius. So you can see here, the condenser is at 51 degrees Celsius, and of course there is some refrigeration cycle that's going on, and this is also connected to a refrigerated space which is at minus 30 degrees Celsius. So it takes some work input, of course, and it transfers or it produces some cooling effect. U dot H. Okay, so this is what we have. Now, one thing that's very clear, if this is the case, then COP of actual is equal to 0.8 times what could be the COP of a reversible refrigerator. Look, this is minus 30, which means 243 Kelvin, divided by the difference between source and sink temperature, so 51, and minus 30, which is 81, and this cancels this 3 times. So this is 2.4, correct? So this is 2.4. And how we identify COP of actual cycle? If the cooling capacity of the plant is 2.4 kilowatts, so the cooling capacity is 2.4 kilowatts, so 2.4 kilowatts, then is 2.4 kilowatts, then the power input to the refrigerator, so W dot in, that is what they are asking you for, correct? So since this gets cancelled, 2.4 and 2.4 gets cancelled, your W dot input means the power that you require for this actual refrigerator to run is 1 kilowatt. Okay, so this is the actual power that you require here in this case. So 1 kilowatt. 1 kilowatt is there in the first option, so that's the correct answer here. Okay, it's 1 kilowatt. It's a bit of simple calculations. You know, 81 times of 3 is 243. So that's a bit simple question. But of course, you could see it's been asked for 2 marks. Let's go for the next question. An A standard diesel cycle with a combustion ratio of 16 takes air at 1 bar and 300 Kelvin. If the maximum temperature in the cycle is 2100 Kelvin, then the thermal efficiency of the cycle is dash percentage. The ratio of the specific heat capacities of air is 1.4. So some data is given. Of course, the cycle is a standard diesel cycle. So if you'd like to draw a standard diesel cycle on a PV indicator diagram, then if this is your, let me use some diagrams here. So if this is your combustion volume, and of course if this is your swept volume, or in general the total volume, because we denote this with total volume Vt, and the difference between these two is swept volume actually, then how does the diesel cycle look like? You have an isentropic combustion initially. Okay, let me draw using different colors so you can identify what are the processes. So this is an isentropic combustion. Then once the combustion is done, or else let me draw a steeper curve so you can feel the things. So this is your isentropic combustion, and in diesel cycle you have a cutoff ratio to which you just supply the fuel, and then we have an isentropic expansion, and then finally we close the cycle with a constant volume heat ejection. Correct? So here this is the cycle 1, 2, 3, 4. This is the A standard diesel cycle. Of course, there is some heat ejection also. Now, if this is the cycle, one thing that's mentioned here, it has a combustion ratio of 16. And what is the combustion ratio? The ratio between the actual volume to the volume that we compress. So Vt by Vc. This is actually in terms of 1, 2, 3, 4. If you write, this is V1 by V2. This is equal to 16. Correct? And the air takes at 1 bar and 300 Kelvin. So P1 is equal to 1 bar, which is 100 kilopascals. And what's the temperature? Initial temperature T1, which is 300 Kelvin. Okay. Then they are asking you for if the maximum temperature in the cycle is 2100 Kelvin. It's obvious. This is the point of maximum temperature. So T3 is given, which is 300 Kelvin. Correct. Oh, sorry. T3 is 2100 Kelvin. So I'm sorry. T3 is 2100 Kelvin. So then the thermal efficiency of the diesel cycle. The thermal efficiency of any diesel cycle is given by, of any A standard diesel cycle is given by 1 minus R power gamma minus, 1 minus 1 by R power gamma minus 1 into rho power gamma minus 1 divided by gamma into rho minus 1. Let us write this gamma a bit neatly. So gamma into rho minus 1. This is what we have as the efficiency of a standard diesel cycle. Correct? Of course, your rho is the cutoff ratio and R is your combustion ratio, and of course gamma is the ratio of specific heats. Now what is rho? Rho is nothing but V3 divided by V2. V3 divided by V2. Okay? If you could identify what is rho, that's it. Your combustion ratio is known, 16 is given already, and of course gamma is also known. So the only thing that you need to get is what is this rho. How you will identify what is this rho? Can anyone tell me what's the sense? How can we find this rho? Because some people are online. So can anyone respond? How we will find this rho? We can just make a little manipulations. Look, this V3 and V2. This is a constant pressure process. Correct? If the process is constant pressure process, then you have V is directly proportional to T. So V3 by V2 is nothing but T3 divided by T2. And what is the value of T3? So you need to know what is T2. And Tv power gamma minus 1 is equal to constant for the process 1 to 2. So for process 1 to 2, Tv power gamma minus 1 is equal to constant. So T1 V1 power gamma minus 1, this should be equal to T2 V2 power gamma minus 1. So this implies your T2 or T1 by T2 is equal to V2 by V1. Or else if you reverse the things, T2 by T1 is equal to V1 by V2 whole power gamma minus 1. Correct? This is what we have. And V1 by V2 ratio is nothing but 16. It's given already. So 16 power 0.4, because the specific heat ratio is 1.4. So T2 is equal to T1, which is 300 Kelvin. So 300 into 16 power 0.4. This is the value of T2. Let us calculate what is T2. So 16 power 0.4. 16 power 0.4 into 300. So T2 value is 909.429. Okay. So 909.429 is T2. So 2100 divided by 909.429. This is your cutoff ratio. Correct? And what is the value of this? What is the value of this? 1 by x into 2100. So this is your cutoff ratio 2.309. So let us calculate this 2.309 as your cutoff ratio. So you have all the data that's needed here. You know what is R, 16. You know what is rho, which is 2.309, and also you know what is gamma, which is 1.4. So let us quickly calculate all these things. So gamma, rho power gamma minus 1. So let us store this value. So rho power gamma minus 1, okay, divided by gamma into rho minus 1. So this is the value. Of course, this has to be now divided with R power gamma minus 1. So this has to be divided with 16 power gamma minus 1, which is 0.4. This is the value that you need to divide. So negative of this plus 1. So this is 0.599. So if you write the value in percentage, we get this thermal efficiency is equal to 0.599. So 59.9. And what's the next digit? Let us write 1. Okay. So 59.91% is the thermal efficiency of this cycle. So 59.91 is the correct answer in this case. 59.91. Okay. So calculations and all we are doing in front of you just to make sure that the answers are correct. Okay. And please be focused. If we are committing any calculation mistakes, please let us know. Okay. And 16 questions are done. So there are only 6 more questions. Let us go through the things quickly. So this is one question that is with us. Air at a pressure of 1 megapascals and 300 Kelvin is flowing in a pipe. Okay, so there is one pipe. This is a pipe, and there is some air that is flowing here. Okay, so there is some air that's flowing here. So this pipe. Okay, and this air is at 1 megapascals and 300 Kelvin. Okay. Then an insulated evacuated rigid tank is connected to this pipe through an insulated valve. Okay. So there is some opening of this pipe and there is a container, or it's given a rigid evacuated tank. Okay. So there is one tank which is of course evacuated, means initially there is nothing inside this tank, and of course this tank and pipeline are connected with the help of a throttling valve in general. Okay. So there is some throttling valve. Now, the volume of the tank is 1 meter cube. So, this tank has a volume of 1 meter cube. So, of course, this is the rigid anyhow. This is a rigid. Okay. And of course, it's insulated as well. It's clearly given. It's an insulated tank here. So, this is insulated. So, this is insulated. Okay. So, the volume of the tank is 1 meter cube, the valve is opened and the tank is filled with air until the pressure in the tank is 1 megapascals. Of course, when this is a supply of 1 megapascals, then if you keep the tank open, if you keep the valve open, some air from here will fill this tank, and of course then the pressure or the air transfer or the gas transfer happens till the pressure equilibrium, since there is some mechanical equilibrium. So, if this is 1 megapascals, the final pressure of this tank, of contents in this tank will also be 1 megapascals. Okay. Then what is the case? Subsequently, the valve is closed after there is some mechanical equilibrium. Consider air to be an ideal gas, okay, and neglect bulk kinetic and potential energies. The final temperature of air in the tank is. So see here, look, if I take this tank as control volume, look carefully, look very carefully. If this tank is my control volume, now for control volumes, if you write the steady flow energy equations, of course, if you write the unsteady equations, generally if you write energy conservation equations, we have energy inlet minus energy outlet plus energy generation rate. This summation should be equal to rate of change of energy of the system. Correct? Or let us write in simple terms instead of writing in differential, since we have mentioned complete things here. This is equal to delta change in energy of the system. This is the basic fundamental equation for any systems, correct? Of course, in case of steady flow analysis or steady flow energy equations, we neglect this because we assume that energy is constant and it doesn't change with time and all. So, of course, that is zero. But here, this is the case of unsteady state heat transfer or unsteady state mass transfer generally. So, this term is retained, but of course, this E generation is zero because this tank is not generating any energy. Similarly, this energy going out of the tank is zero because this tank is rigid and also this is insulated. So, there is no possibility that this tank has some displacement work or it transfers some energy. So, one thing from this equation that you can obtain is E dot in, or some energy that is flowing in. That's nothing but the change in energy of the system. Correct? This is what we can write. So, what is the energy that's coming in. Look, there is some flow here. Here there is non-flow because this is a tank and it's fixed. But from the pipeline to here there is a flow, which means the fluid which is coming inside is bringing in some enthalpy with this. So this implies energy that's coming in is nothing but mass flow rate inside into enthalpy that's taking in. And you know, since if you treat A as an ideal gas, enthalpy at the inlet is nothing but Cp into T inlet. This should be equal to change in energy of the system. Initially the energy of the tank is 0 because the tank is evacuated and there is nothing inside the tank. So what will be the change in delta E, which is nothing but final minus initial. So since initial is 0, this change in energy of the system is nothing but final energy of the system, which is again m dot in, because whatever the mass that's coming in, that's only settling inside. So the specific energy of this, or the energy of the tank, is nothing but Cv into T final. This is what we have. So m dot in gets cancelled, and Cp by Cv is gamma, and T final is nothing but this Cp by Cv, which is gamma times this T inlet. Okay, this is what we have. So this is the final relation. Okay, this relation I have shown you because this is very much important, and this being asked in many exams. Okay, so that's why this is very important. So T final is equal to gamma times of Tn. Whenever there exists some mechanical equilibrium, means if here this pressure is 1 megapascals and if here this pressure is also 1 megapascals, or if here it is P1 and then here also finally if it's P1, then definitely the final temperature of the tank is nothing but gamma times of this initial temperature, okay, which is the inlet temperature. So here gamma is given, which is gamma is directly given or not given. So Cp is given, R is given. So you can evaluate what is Cv, and Cp by Cv is the value of gamma. So let us calculate Cv. Let us clear the memory and all. Okay, so 1.005 is Cp minus characteristic gas constant, which is 0.287. So this is the value of your Cv, correct? If this is your Cv, so 1 by Cv into Cp we can calculate 1.005. So into 1.005. So this is the value. 1.399 is gamma. So gamma into what is the initial temperature at which it's coming? 300 Kelvin. So into 300. This could give you 419.91. Okay, so let us write T final is equal to 419.91 Kelvin. If you want to approximate to nearest integer, you can write 420 Kelvin. Okay, so anyhow this is Kelvin, so 419.9 Kelvin. So this answer is 419.91 Kelvin. And if you write 420, that's not even wrong, because for A, if you make certain calculations, this will be 1.4. Okay, next let us go for this question. Two A streams of mass flow rates m1 dot and m2 dot enter a mixing chamber and exit after perfect mixing. The corresponding temperatures of the inlet streams are T1 and T2 respectively. Heat loss rate from the mixing chamber to the surroundings is Q dot. Assume that the process is steady. This is important. Assume that the process is steady. Okay, so there is some steady process that's happening. Specific heat capacity is constant. This is also good, which means we can treat the substance as ideal gas, and A behaves as an ideal gas. Of course, this is a perfect gas, and of course that's a subclassification of ideal gas, so it's an ideal gas. Identify the correct expression for the final exit temperature T3 after mixing. The mass specific heat capacity of the gas at constant volume and at constant pressures are Cv and Cp respectively. Of course, we know these are the specific heat ratios. Specific heats. Neglect the bulk kinetic and potential energies of the streams. Look, it's a very nice question, but of course again a very simple question. So please see here. Let us try to frame some diagram for this. Okay, so see here. So this is your two branches that's flowing in. Okay, this don't want to go from here. Okay. So this is your branches, two A streams mixing. Now one thing is very clear, two A streams of mass flow rates m1 dot and m2 dot. So you can see, let us draw this. So this is your m1 dot that's going in, and of course this is your m2 dot that's going in, and finally you will be having your m3 dot that's coming out, correct? So m1 dot, m2 dot and m3 dot. This is what we have. Now see carefully. They are telling you it is not insulated because there is some heat interaction Q dot that's happening between the mixing chamber and the surroundings. So some heat is going out, Q dot, and this is rigid, of course, so there won't be any work interactions, and they have also asked us to neglect the bulk kinetic and potential energies of the streams. So they have asked you to neglect potential energies and kinetic energies of bulk in these streams. So now let us try to solve this. If you apply the steady flow energy equation, we have Q dot minus W dot is equal to delta Ke dot plus delta Pe dot plus delta H dot. This is with us, and this chamber is rigid, and neglect bulk kinetic and potential energies is also given. So this is what we are left with. So Q dot is equal to delta H dot. So Q dot can be written as final enthalpy minus initial enthalpy. So final enthalpy can be written as M1 dot plus M2 dot, because this is the total mass flow rate that flows out. Look, this is M1 dot and if this is M2 dot, and meanwhile there is no mass generation or no mass escaping. So definitely M3 dot should be equal to summation of these two, M1 dot plus M2 dot. Next, if you know this, then what could be the specific enthalpy? Cp into T3 minus summation of initial enthalpies. Initial enthalpy of this stream, which is of mass flow rate M1 dot, so M1 dot into CpT1, correct? So M1 dot into CpT1 plus M2 dot into CpT2, because this is something that's entering inside. So now from this expression we need to identify what is T3. That's a simple. So M1 dot plus M2 dot into Cp into T3. Let us write M1 dot plus M2 dot into Cp into T3. This is equal to Q plus M1 dot into CpT1 plus M2 dot into CpT2. But of course, again, one correction that need to be done here. Look, what is that correction? It's clearly given heat loss rate from the mixing chamber to the surroundings, means there is some heat loss initially, which means this Q which we are writing here is negative, correct? So this is negative. So let us write this. So Cp or T3, if you write directly, T3 is equal to minus Q dot, because rate is given, so minus Q dot divided by M1 plus M2, of course, mass flow rates into Cp plus this Cp, if you gets cancelled, then M1 dot T1 plus M2 dot T2 divided by M1 dot plus M2 dot. This is the expression. Okay. Vignesh Khanna, so sir, why changed fluid mechanics timings from 9 into 12 p.m.? 9 into 12 p.m. in YouTube? No. Generally, yeah, I was about to tell that at the end of this lecture, we are starting a fluid mechanics batch, which is of course absolutely free. Okay, it's a comprehensive course on fluid mechanics. Of course, I'll give you enough information at the end of this lecture, since only some I think some 5 questions, okay, 4 questions are left, because this is the 18th question already and it's done. So this is the final temperature T3 in this case. So we have only 4 questions. So after these 4 questions, I'll give you enough information when we are starting this fluid mechanics batch, and of course when it's absolutely for free again, and you need not pay anything, of course, and we'll be covering the topics that are in XC syllabus as well. Okay, so no issue. Anyhow, M1 dot plus M2 dot. So now if you see, this option is somewhere here, third option, correct? M1 dot plus T1 plus M2 dot T2 divided by M1 dot plus M2 dot minus Q dot divided by M1 dot plus M2 dot into Cp. Of course, here this is Cp. Clear? So this is the final expression for the temperature T3. It's just steady flow energy equation analysis. Okay. Next, there are only 4 more questions. Let us do the things quickly. So 19th, air having a mass flow rate of 2 kg per second enters a diffuser. Okay, so there is some diffuser. There is some diffuser which is an inverse operation of nozzle. So mass flow rate that's entering in is 2 kg per second. So mass flow rate is equal to 2 kg per second that's entering inside at 100 kilopascals and 30 degrees Celsius. So P1 or P inlet is equal to 100 kilopascals and T1 is equal to 30 degrees Celsius, which is 273 plus 30, which is 303 Kelvin. Okay, this is what we have with a velocity V1 of 200 meters per second. So V1 is equal to 200 meters per second. And in diffusers, you know, generally these velocities are very much less when compared to this velocities. Anyhow, let's go through. exit area of the diffuser is 400 centimeter square. So A exit, this is equal to 400 centimeter square, and this is nothing but 4 into 10 power minus 2 meter square, correct? Because this 100 and 10 power minus 4 gets cancelled 2 times, 10 power minus 2 times, so this is 0.04 meter square, okay? Then, while the exit temperature of the air is 45 degrees Celsius, so T exit is also given, which is 45 degrees Celsius. And in 45 degrees Celsius, of course, this can be converted to Kelvin, so 8, 4 plus 7, 1, 3, 18 Kelvin, correct? 273 plus 45, 273 plus 45 is 318 Kelvin, okay. The rate of heat loss from the diffuser to the surroundings is 8 kilojoules per second. So during the movement of gas, there is some heat loss, which is Q dot. Of course, this is 8 kilojoules per second. So if this is 8 kilojoules per second, the pressure at the diffuser exit means here, the pressure at this exit is what? In kilopascals. And some properties of the gas is given. For A, characteristic gas constant is 287 joule per kg Kelvin, of course, and specific heat capacity at constant pressure is 1005 joule per kg Kelvin, and assume air to be an ideal gas and the flow to be steady. Okay, so basically one thing is given at the end, the flow from along the diffuser, the flow in the diffuser is steady. So if things are steady, we can apply steady flow energy equation, correct? So let us apply the steady flow energy equation that is with us. So if you apply the steady flow energy equation, we have Q dot minus W dot is equal to delta Ke dot plus delta Pe dot plus delta H dot. This is what we have, of course. So now diffusers are a visit, so they don't do any external work, and of course neglect potential energies because there is no difference in the datum heads in both the sections, correct? So that's we can take. Then what do we have? We have Q is equal to 8 kilojoules of second, but of course this is heat loss from the diffuser, so we'll assume this is minus 8 kilojoules, so minus 8 into 10 cube is equal to delta Ke, which is 2 kgs per second into half mv square, so half into mass flow rate, which is 2 kgs per second, so let us write properly, half into 2 kgs per second into C2 square minus C1 square, C exit square minus C1 square, which is 200 square, plus potential effects are neglected, again delta H, which is 2 kgs per second into Cp, which is 1005 joule per kg Kelvin into T2 minus T1. So what are the temperature differences that I mentioned? So what are the temperature differences mentioned? This is 318 and that's 303. So basically it's 45 and 30. So it's 15 is the temperature difference. So let us calculate C exit from this. Okay, 2 gets cancelled anyhow, of course. So let us calculate a few things. If you shift this to the other side, minus 8000 minus 30 into 1005. This plus 200 square. This is equal to velocity exit. So C exit square. So let us calculate this value quickly. Minus 8000 minus what do we have? Still 30 into 1005. 30 into 1005. Or since this is also in joules, let us enter 1005. Okay. So this is what we have. Of course, plus 200 square. Plus 200 square. This is the value 1850, and if you take the square root of this, 43.011. So this C2 or C exit is equal to how much is this? 43.011. So 43.011 meters per second. So this is the exit velocity. Now if this is your exit velocity, since mass flow has to be conserved, so m dot in should be equal to m dot out. Correct? So if this is the case, 2 kg per second is flowing in. So this is equal to density at exit into area of exit, which is 0.04 into this velocity square. Rho A V square. Sorry, density into area into V. So this is the mass flow rate. So V is 43.00. 43.011. So let us calculate this value. We'll get what is the density of exit. Density of exit, let us calculate 2 divided by or else 1 by x into, let us calculate the values quickly, 2 divided by 0.04, 2 divided by 0.04 into 43.011. So this is your density 1.1624, reasonably correct. So 1.1624 kg per meter cube. So we know since this is an ideal gas, we can apply the ideal gas equation. So P naught is equal to rho R T naught. So this P naught can be calculated from here, which is rho, which we already have just now, 1.1624 into the characteristic gas constant is given here. You can see characteristic gas constant is 287, or since the answer is in kilopascals, let us enter this in kilojoule per kg Kelvin. So 0.287 into exit temperature. What is the exit temperature that's available? 318 Kelvin. So 318 Kelvin. So this implies your P naught is equal to, so let us calculate this value, into 0.287 into 0.287 into what's the other value that you have? 318. So 318. Okay. 1.1625, let us take 1.1625 into 0.287 into 318 Kelvin. So this is 106.09, 106.096. Okay, so 106.096 kilopascals. So this is the exit pressure of the diffuser. Okay, since this is the numerical class type question, it includes two steps basically: calculation of C exit, then O exit, and finally we get the value. Okay, so 106.096 is the correct answer in this case. So 106.096 kilopascals. Okay, so this is what we have. Let us go for the next question. 20th question. If H is the mass specific enthalpy, S is the mass specific entropy, P is the pressure, T is the temperature, CV is the mass specific heat at constant volume, similarly Cp at constant pressure correspondingly, beta is the coefficient of thermal expansion, okay, V is the specific volume, mass specific volume, K is the isothermal compressibility. Then the partial derivative of dou H by dou S at P. Look, these TdS equations are valid for any substance, correct? So if you have this TdS relation as TdS is equal to dH minus VdP, then this expression dou H by dou S at constant pressure, at constant pressure this derivation of P is 0, correct? So at constant pressures this dP is 0, which means your TdS is equal to dH, which means you have dH by ds at constant P. This is always equal to your temperature. Okay, so this is nothing but T. Of course it's absolute, so this is T, which is given here. It's T is the absolute temperature. Of course this is the temperature. Okay, so T is the correct answer in this case. Okay, one thing that I need to tell you here, this is also geometrically nothing but the slope of HS diagram, correct, at constant pressure. And you know, at constant pressure lines, the slope of HS means the Euler diagram gives you temperature. Yes or no? Dou H by dou S at P is nothing but your T. Clear? So this is your temperature always. Let us go for 21st. This is also a very simple question. 4 different entropies, S, temperature, T diagram. So basically 4 ST plots are given representing liquid to vapor phase transition process of a pure substance in a closed system under constant pressure as shown. Of course, during the phase change for a pure substance, pressure remains constant. The diagram which correctly represents the process. Look, if this is your TS plot, we have done in the beginning of the class also today. If this is your TS plot, your substance takes this form, correct? Whenever you are having some constant pressure, then it takes this form, correct? So one thing is very clear, even if you tilt this diagram so that this S goes to the top and T goes to the down, this is the correct case of this diagram. Yes, because you can see clearly these two lines will be always parallel. They are not like intersecting, correct? Means in the least case, like of course this line is not exactly parallel, but of course for any ideal situation we can take these two lines are parallel, which is not the case in any of this. Okay, but of course you can have a chance of this option D also, because these two lines are intersecting actually. You can see if you project, these two lines intersect, but in actual case these two lines are to be parallel, correct? So which means these two are wrong. Now why this option is wrong? Look, as your temperature is increasing, your entropy is decreasing. Is this possible? If your temperature is increasing, definitely your molecular motion increases and your entropy increases. But here there is a case that your temperature is increasing but your liquid entropy is decreasing, which is not the case here. So this is wrong and this is correct option. Okay, so first option is correct. So first option is correct. Okay, the only logic is these two lines don't intersect in general, correct? But here in these two diagrams the lines are intersecting, of course, and here in these two diagrams, here you have as temperature is increasing, your entropy is decreasing, which cannot be the case. So this is wrong and this is always correct. So let's go for the last question of this module. This is the last question that we have. So a cylinder of volume 1 meter cube. Let us write the solution of this. A cylinder of volume 1 meter cube contains a mixture of CO2, 20% by mole and O2 80% by mole at 100 kilopascals and 300 Kelvin. So there is one cylinder. There is one cylinder in which there is 20% mole of CO2 and of course 80% mole of oxygen. Okay. So what is the total pressure of the tank of the cylinder? P is equal to 100 kilopascals. Okay. Next, volume is given. V is 1 meter cube. And what is the temperature at this situation? 300 Kelvin. Okay. This is fine. Next, this cylinder is connected to a 1 megapascal pressure line carrying nitrogen at 300 Kelvin. The cylinder is filled isothermally till the pressure of the gas mixture inside becomes 500 kilopascals. Now, what they have done, they have introduced some nitrogen into this. They have introduced some nitrogen into this. Look, when they introduce some nitrogen into this, then the total, what are the final situations? P1 or P2 is equal to 500 kilopascals. Then volume remains fixed, 1 meter cube. And what is the temperature, final temperature? Look, it's clearly given. This cylinder is connected to a 1 megapascal pressure line carrying N2 at 300 Kelvin. The cylinder is filled isothermally till the pressure of the gas mixture inside becomes 500 kilopascals. So whenever the cylinder is getting filled isothermally, that means the initial state and the final state of the final initial and final temperatures of the system are same. So which means again your T is 300 Kelvin. So let us suppose total number of moles in this case is N1 and total number of moles in this case is N2. Of course, V2 and T2. So now, since this is also a mixture of ideal gases, look, let us suppose there is total some 100x moles of substance inside this. Okay, so total, let us suppose 100x moles of substance is lying inside this tank. Now, which means 20x moles of CO2 we have and 80 moles of, 80x moles of, this is CO2 and of course this is O2. So to this, there is some nitrogen that is also added and we want to find what is the amount of nitrogen that is added here. Correct? This is the case. Now, since both are mixtures of ideal gases, can we write temperature 1 is equal to temperature 2 because tank is filled isothermally? Can we write? So, if you apply ideal gas equation individually for both the cylinders, we have P1 V1 by total number of moles, which is N1 R bar. This should be equal to P2 V2 divided by N2 R bar. Correct? And you know, in both the cases, this universal gas constant is constant and this volume of the tank is also constant. Basically, volume of the cylinder is fixed. If this is the case, then P1 divided by P2. Initially, the pressure is 100 kilopascals and finally the pressure came to 500 kilopascals. So, 100 divided by 500. 100 divided by 500. This is equal to P2, N1 divided by N2. So, N1 is the total number of moles in this gas, which is 100 times of X divided by N2, which is the total number of moles in this case, which we are denoting currently by N2. So, you can clearly see these two zeros gets cancelled. So, N2 is 500 times of X. So, total number of moles of substance here is 500 times of X. Okay. So, if this is 500 times of X, look, some nitrogen is being added. Nothing inside the system is taken out. Whatever is existing, we just added some more thing for that. Correct? So, can you tell me or can I tell the difference between N2 and N1 is the number of moles of nitrogen that came in? Yes or no? So, the number of moles of nitrogen that came inside is nothing but initial number of moles and final number of moles. The difference between these two things, 500x minus 100x, which is 400 times of X. So, if you find what is the value of this X, then your story is done. Look, to find this, given initial pressure is 100 kilopascals and 0.2% mole fraction is present in this substance of CO2. So, see here, if you apply Dalton's law of partial pressure, if you apply Dalton's law of partial pressure for this CO2, then we can write partial pressure due to CO2 into volume of the tank. This is equal to number of moles of CO2 into R bar into T. Correct? This is what we can write. So, partial pressure of CO2, which is the mole fraction of CO2 into total pressure, which is 100 kilopascals. Correct? Total pressure is 100 kilopascals initially. We have written here. Yes. This should be equal to number of moles of CO2, which we have denoted with 20x into R bar into 300. Because your initial temperature is 300. So, let us calculate few things from here. So, this 0.2 into 10 gets it 2 and this is 10. So, 10 again gets cancelled. And So your X is nothing but 1 by 300 R bar. So the value of X is 1 by 300 R bar. So let us calculate this value. Number of moles of N2 that's available is equal to 400 into 1 by 300 R bar. And this is equal to 400 by 300. Look, here we made one small thing. One small mistake actually. To be frank, it's a mistake. This is in kilopascals, but the moles we are taking is only moles. They are not kilomoles. But because R is 8.314 kilojoules per kilomole Kelvin, we need to write this pressure also in pascals actually. So we write into 10 cube. We can write here. Correct? So there will be one 10 cube that's left over. So here we'll be coming. We'll be multiplying with a 10 cube, and of course here there is a 10 cube, and again we have a R bar which is 8.314. So let us calculate this value. This is 4 by 3 and 4000 by 3 R bar. So let us calculate this value. 4000 divided by 3 into R bar, which is 8.3145. Let us do this. So 160.36. So 160.36 moles of nitrogen is injected or inducted into the system. So total number of moles that got transferred into the system is 160.36 moles. Clear? So these are the answers of all the thermodynamics questions that came in GATE 2021 XC. So we answered all the 22 questions, and I hope you don't have any doubts here. Clear? So this is what we can do. Next, I would like to tell you something. There is something that we would like to give, as we always give for free. So in YouTube channel of Engineers Hub, you can find the courses of engineering mathematics and thermodynamics completely free. Correct? And we want to add one more feather to the cap. So we are starting this fluid mechanics. And it's a comprehensive course. Okay, means we'll be dealing all the basic theory points, and of course we do few problems as well, so that we try to cover the complete syllabus of mechanical, civil, XC, PI, CH. Okay, because all these syllabuses are very much common to mechanical, but of course some 5-10% variations depending on the branch. So we are going to take care of that special topics even, and of course we are going to complete this complete fluid mechanics in the YouTube channel for free. Okay, next, there is one more thing that I would like to tell you. We are going to start this course from 1st of March 2021, which is exactly 1 week from now. But of course, the timing will be from 9:30 p.m. and the class will be for 1.5 hours. So 9:30 p.m. to 11 p.m. we'll be having a class daily. Okay, on fluid mechanics. So please don't miss the class, and please try to maintain some consistency. Okay, and also you can see we have launched an Infinity app. We are the one who came with the test series of XC for GATE 2021. And after the exam, we felt happy that many of the students are replying back that questions replicated from the test series in actual GATE examination. We felt very happy for that as well. So now one important thing is, you please try to install the Infinity app, because daily we are posting some practice questions which are for free. Okay, so if you practice some questions daily, hydraulic machines also covered. Yeah, we'll try to cover this hydraulic machines as well. No issue. Okay, Kapil. So now one important thing is, please try to install this Infinity app, because we are uploading some free questions, free test series in that Infinity app daily. And if you practice some questions daily, you will be getting in touch with the concepts, and finally you will be able to do better. Okay, because you won't forget the concepts. So I hope we have covered good enough. So is there any doubts to anyone at any point? If there is no doubts, it's getting to be 11, so we'll end the session. Clear? Is that okay? So shall we end the session? Okay, then thank you all. Have a nice time. So these are the solutions of XC thermodynamics is concerned. Okay, thank you all. Have a nice time. We'll see you all on March 1st at 9:30 p.m. sharp on the same channel of Engineers Hub. Thank you all.